the quantization of angular momentum, and we'll try to derive the formula for the energy. So let's start with an electron revolving around a proton. So we'll try to find what is the total energy of the orbiting electron. So I would start with the total energy. So I would write here the total energy of the orbiting electron, the total energy of the orbiting electron. So total energy of the orbiting electron, and let's say this we represent by ET. So I would write here ET is actually equal to the kinetic energy, which is half mv squared, which is half mv squared, added to the potential energy, which is negative. So I would write negative k e squared over r, and let me put this within bracket. So this is the total energy, but we know that the electron is moving in a circular path and it is acted upon by an electrical force. So using the concept of circular motion, we could write k e squared over r squared. So we could have k e squared over r squared is equal to actually mv squared over r is equal to mv squared over r. It's technically saying that the centripetal force, which is mv squared over r, is balanced by k squared over r squared. Now from here, what are we going to deduce? We are going to deduce that mv squared is equal to mv squared is actually equal to k squared over r, k e squared over r. Um, so now the total energy, so technically the total energy becomes, so I would say the total energy is total energy is, so I would like to again represent this by ET, which is equal to, now half mv squared, here you see you have the half mv squared, and we know that mv squared is k squared over r. So I would replace mv squared with k squared over r. So I could write ke squared over twice r added to within bracket within negative sign k e squared over r, and that gives you negative, half k e squared over r. So far we have derived that the total energy is negative k e squared over r. Now here Bohr made an assumption, and his assumption was technically, so here I would write we use the Bohr's assumption. So we have the Bohr's assumption, and the Bohr's assumption was the angular momentum, which is mvr is actually equal to the integral multiple of h over 4 pi. So I would say the integral multiple, so I would write n h over 4 2 pi. So it is like his assumption was the angular momentum, which is mvr, is an integral multiple of h over 4 pi. So technically you could write mv squared over r is actually equal to nh by 2 pi. So from here we will have what we'd do is that we'd square both sides. So I would say m squared v squared and r squared is actually equal to n squared h squared over 4 pi squared. And from here I would derive what is mv squared. So I would say mv squared is actually equal to n squared h squared over 4 pi squared and m times r squared. So what I did was that I just played around with this equation, and I had m squared v squared r squared, which is actually equal to n squared h squared over 4 pi squared. So I made mv squared as the subject, and I got n squared h squared divided by 4 pi m r squared. Now let me go to the next page. So now we already calculated that mv squared over r, mv squared, sorry, just mv squared, we calculated mv squared is equal to ke squared, ke squared over r. If you realize, we did this in the very first part where we said mv squared is equal to k squared over r. Now substituting mv squared, we would get now mv squared as substituting mv squared as ke squared over r, we could get ke squared over r, ke squared over r is actually equal to n squared h squared over 4 pi squared m r squared. Now what did we do actually? Here we, in the beginning we had got mv squared over, mv squared is k squared over r, and if you realize in the last equation we had mv squared is n squared h squared divided by 4 pi squared m r squared. Now what I did was that we tried to equate both of them, so that mv squared is k squared over r, and here we have mv squared equals to n squared h squared divided by 4 pi squared m r squared. We tried to equate both of them, and we got this particular expression, which is ke squared over nh squared, k squared over r equals to n squared h squared over 4 pi squared m r squared. Now from here what are we going to do is, from here we are going to derive the expression for r. So therefore r is going to be, if you rearrange this, you will realize that r is going to be h squared divided by 4 pi squared k e squared m times n squared. Now we have got an expression for r, so we could sub in the numbers and get the actual value for r. So here h, h is Planck's constant, so I would write here this is 6.626. You could get these numbers from the data booklet, multiplied by 10 raised to the power negative 34, and I could put the brackets here, and this is squared, and then I divide this. So then we have 4, and this is pi squared, and this is k. The value for k from the data booklet, if you see, it comes out to be 8.988. It is 8.988 multiplied by 10 raised to the power 9, multiplied by 10 raised to the power 9, and multiplied by, so we got the value for k, but then we have the square of the charge of an electron, so I would write here 1.6 times 10 raised to the power negative 19, and then square that number multiplied by the mass of the electron, which is going to be 9.109 actually, to get the actual number, 9.109 times 10 raised to the power negative 31. And let me complete this so we don't have any confusion. And this is further multiplied by n square, so I would write here this is equal to n square, sorry, multiplied by n square. And we come to the next slide. Oops. So when we solve, we actually get the value for r as r, we are going to get it as 0.5 multiplied by 10 raised to the power negative 10 n squared meters. Now we got the value for r. Now what are we going to do is, we have the formula for the total energy. If you realize, in the beginning we calculated the formula for total energy. So ET we had calculated as negative half ke squared over r. Now what I'm going to do is that I'm going to sub in the value for r from this equation. Here you see r I got as n square h square over 4 pi squared ke squared m. So I'm going to sub in the value for r here, and I'm going to get ET. So I'm going to get ET. How about I write here? R, and we had already calculated r as h square over 4 pi squared ke squared m multiplied by n squared. So I'm going to sub in this value for r. I'm going to sub in this value for r here, and what I'm going to get is, I will be getting ET is equal to, so I would say negative 1 over 2. This is going to be ke squared, and instead of r, if I sub in, this is as n square h squared multiplied by 4 pi squared ke squared m. And I'm going to rearrange this. So if I rearrange this, I will ultimately get negative 2 pi squared, I'm getting from here because I cancelled this 4 by 2, so I got negative 2 pi squared, and ke squared m. So this is actually k and k are multiplied, so that becomes k squared, and m times e raised to the power 4, because this e and this e, so e squared and e squared, they are multiplied, so you get 2 pi squared m k squared e raised to the power 4 divided by h squared, and I would write here 1 over n squared separately. So you get the total energy. Now what I'm going to do is, I can write this expression as ET. I can write this expression as ET is actually equal to negative c multiplied by 1 over n squared. Now you understand why I wrote this 1 over n squared separately. So I wanted to make sure I have one complete um, expression here. So I got negative 2 pi square k square m e raised to the power 4 over h square, and I wanted to separate this n square. So ultimately, you see, I'm going to take this as capital C, so I'm going to put this as negative c times 1 over n square. So technically you will have c. If I see the value for c, you see you get the value for c as as 2 pi squared k squared e raised to the power 4 m over h square. So I would write this as 2 pi squared m e raised to the power 4 e raised to the power 4, and this is k squared divided by h square. So how about I sub in the values and get the value for c. So c is going to be 2 times pi squared multiplied by the mass of the electron, which is 9.109 times 10 raised to the power negative 31, and this is multiplied by the charge of the electron raised to the power 4. So I would say 1.6 times 10 raised to the power negative 19 raised to the power 4 multiplied by k squared, which is 8.988 times 10 raised to the power 9 times 10 raised to the power 9 squared, and this is divided by the number which is h square, which is 6.626 times 10 raised to the power negative 34 squared. And if you solve these numbers, you are going to get c equals to 2.170 multiplied by 10 raised to the power negative 19 joules. And I want to convert this into electron volts, so this is going to be 13.6 electron volts, 13.6 eV. So you see, I got the value for C as 13.6 eV, but I had the total energy. If you realize, I had the formula for the total energy as negative C times n squared. So I would write here now E is going to be equal to we had negative 13 over 0.6, negative 13.6 divided by n square electron volts. So this is how we derive the formula for total energy, and this was done by Niels Bohr.